So now I am going to talk about Boxplot. Boxplot is a very good summary of a data because it provides 5-number summary. 5-number summary means minimum, then first quartile, then second quartile, that is median, then third quartile, and then maximum. So this 5-number summary is the best summary of a data. This concept of box plot was introduced by John Tukey, a great statistician. So here we are going to simulate a data from Weibull distribution, about which we have just we had talked in our previous video. So y is equal to r Weibull, 1000 observations are being simulated, shape is equal to 1.5 and scale is equal to 50. So we are simulating observations see, and if we want to look to the data, so these are the observations, 1000 observations from Weibull distribution with shape is equal to 1.5 and scale is equal to 50. If we want to make a histogram is this. This is the histogram. So histogram of the data shows it is right skewed. It is right skewed distribution. So how this can be summarized? This shape can be summarized using box plot. So I am going to draw box plot and horizontal is equal to true. So if we see, this is the box plot. This is the box plot. So here these observations are extreme right, they are outliers, and this is the length of the box shows the variability present in the data. The beginning of the box is the first quartile and end of the box is the third quartile, and this is the second quartile. This is the second quartile, that is median, and this distance is called whiskers. This distance is also called whiskers. So whiskers are what? Because it is box whisker plot. So first I would like to give you the data about the median. Median is 42 point something. Then quantile, I want to compute quantiles. See, the first quantile is 23.37 and the third quantile is 62.35, and min is 0.25 and max is 0.25, and IQR, interquartile range, is 38. So all these information are given in the box plot. Now lower whiskers, I had talked about whiskers. So lower whisker is nothing but minimum of y plus c. This is the 20.23 point. This is the first quartile. Here it has changed first quartile because it is on the basis of simulated data, minus 1.5 into IQR. IQR stands for, so this is the maximum of minimum of y, and here the first quartile minus 1.5 times IQR, interquartile range. So here actually lower whisker we can compute. This is the lower whisker, 0.32, and similarly upper whisker is defined like it is min of, here we are using max, but here max of y, and then this is the second quartile 60 point something plus 1.5 into IQR, interquartile range of y. So this is the upper whisker, and then we are getting upper whisker. So these things are shown in the box plot. These things are, this is the lower whisker, this is the upper whisker, and this is the first quartile, this is the second quartile, this is the third quartile. The length of, and this length is known as IQR. IQR. If IQR, if box is lengthy, that means there is more variability in the data. If box is small, length of the box is small, that means there is less variability in the data. Now what comes outside this, these are known as outliers. Actually, a theory suggests that if data which lies between, if distribution follows normal distribution, then the 99% observations should be covered under lower whisker and plus whisker. So if data follows normal distribution, so this is a kind of check. Now I am going to talk about box plot of iris data. Iris data is a great data which is available with R. Just help iris. See, this is available with the package data sets. Edgar Anderson's iris data description. The famous Fisher or Anderson's iris data set gives the measurement in centimeter of the variable sepal length and width and petal length and width respectively for 50 flowers from each of the 3 species of iris. The species are iris setosa, iris versicolor and iris virginica. So this is the data, and if we want to look the names of iris, so these are the column names: sepal length, sepal width, petal length, petal width, and this is the column of species. See, if I put head iris, it is the header part. So here first 50 observations are setosa, 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 and then 50 are versicolor and rest 50 are virginica. Say for example, if we want to look into the tail part of the data, 150 observations are there. Iris, see, it is virginica, virginica, virginica. So these are the, so first 4 columns are numeric, whereas the last column, 5th column is character string or factor. We can check its structure. str iris, we can check the structure of iris data. See, here it is a factor with label, 3 labels, setosa, versicolor, and so I have already talked about versicolor. It is a data frame of 150 observations and 5 variables. Those variables are sepal length, it is numeric, sepal width numeric, petal length numeric, petal width numeric, whereas species column is a factor with labels 3. If we want to view the data, we can make use of the function of RStudio view iris. So here we can view the whole data. Here it has the flexibility that you can view the whole data, 150 observations. So this is the iris data. So here we are going to have box plot. See here, names, head, tail, then structure, and then we are going to have box plot of this data. See what this box plot says, that this is the Satosa data, and it talks about sepal length. So sepal length is, this is the median sepal length which is coming in between. This is the lower whisker, this is the upper whisker, and this length of the box shows there is least variability in terms of Satosa, whereas the most variability is in terms of versicolor, and almost equal variability is there in terms of Virginica. So this graph shows actually all the important aspects of box of the data hidden there. Now I'm going to talk about scatter plot or plot of the data. See, we are simulating R norm, 100 observations from normal distribution, and then 100 observations from Poisson distribution with lambda is equal to 30. If we want to get about mean of y, mean of Poisson, it is 30.56. Mean of x should be around 0. SD of x. Now I am going to plot x comma y. On x-axis it is x, and on y-axis it is y, and it is Poisson versus normal. So this is the plot, Poisson versus normal. This is the plot of the data. Suppose we want plotting character 16. So this is with the plotting character 16. Suppose we want type is equal to L. So this is the, and then plot sort x, sort y, and type is equal to L. Both we are sorting. Sort means sorting in increasing order, sorting in increasing order. Both we are sorting, and after that we are plotting them. Plotting from a data frame. Here data orange is a data. See, first I should get help about orange. It is a data set, orange, data with the package data sets, growth of orange trees, description. The orange data frame has 35 rows and 3 columns of records of the growth of orange trees, orange format, and see tree, a column of tree, then age, and then circumference. So this has been discussed by Draper and Smith, and then Pinheiro and Bates. Both of them have discussed this data set orange. So here I am going to talk about orange data. Data orange has been loaded, and then names orange. So these are the trees, age, and circumference. Then header part of the data, we have seen this. and then tail part of the data, we have seen that. Then structure of the data. The structure of the data says that trees is ordered factor and trees is the order factor. And then we can extract trees from orange. Then we can make use of the unique, see 1 1 1 1 is repeating, 2 2 2 is repeating. If we want unique of them, so we have to issue the command unique as dot character orange trees. So it is 1 2 4 5. Plot circumference versus age, data is equal to orange. So this is the plot. This is the plot. Circumference versus age. As age increases, circumference also increases. It is the growth data. Plot circumference versus age, data is equal to orange. Plotting character as dot character trees. So here as dot character tells about, say for example, this is the first tree, this is the third tree, this is the fifth, this is second, this is fourth, like that. And character expansion is 0.75, that expands the character here. Suppose instead of 0.75, suppose I am writing character expansion 2, so that means it will expand the character twice of normal. See, bigger. And if we want to reduce this, say for example 0.5, so here it becomes very small, and that's why 0.75 is a better expansion. 0.75 is a better expansion. ठीक है. Now I am going to talk about qqplot, quantile-quantile plot. Actually, quantile-quantile plot are very important for graphical checking whether data comes from the same distribution or not. So what we do, we plot the quantiles of our observed data on one axis and the other on the quantiles from the distribution on the x-axis. And it is a very good graphical technique to check whether data comes from the same distribution or not. If data are around a linear trend, that means the data supports the distribution. If they are not from the linear trend, data does not support the distribution. So this is the interpretation of quantile-quantile plot. Quantile Z prob is equal to par mf row 1 comma par mf row C 1 comma 4. So that means mf row stands for row wise partitioning of the screen, 1 row and 4 columns. Then we are simulating x is equal to r norm 1000 and then a is equal to r norm 1000, and then we are having qqplot x versus a. So what will happen that since they are from the same distribution, the points must be around a line. And here in the second example, a is equal to r norm, mean is equal to 3 and sd is equal to 2, then qqplot x versus b. So here B is normal distribution with mean is equal to 3 and SD is equal to 2, whereas X is equal to R norm with mean is equal to 0 and SD is equal to 1. So there will be a difference with qqplot. Then C is equal to RT. RT stands for random simulation from T distribution with 2 degrees of freedom. So if we plot qqplot X versus C, see the tails of C are heavier than that of X, and then we can have par MF rho is equal to C11, and that means our screen is returning to 1 row and 1 column instead of 1 row and 4 columns, and then we are adding curve dt, df is equal to 100 from minus 5 to plus 5, and curve d norm add is equal to 2 lt. So these things we can generate by using yes. So these are the 3 graphs, A versus X. So here points are around a linear trend, so that means good fitting. Here B is rescaled to X, but here C has heavier tails, and that's why in the tail they are not around the trend. So C has heavier tail than the X, that is the normal, and that's why this difference comes. So actually these things, suppose we have a data, some other data, suppose for example trees data we have, and we want to see whether it should come. Okay, now next lecture I shall talk tomorrow.